platform team, specifically the compute team, and we handle all of the open source projects that are used in Netflix's data platform. So that includes things like Presto, Hadoop, Spark, etc. I'm more on the Spark side as an execution engine, and then I also get into data formats and how we interact with the underlying file system like S3. And what we're going to talk about today is sort of on the data format side. It's Iceberg, which is our new table format for doing things faster in S3. And that's actually a bit of a lie because it's for doing things faster in HDFS as well. We just thought it would probably get me into the conference if we said it was for S3, because everyone knows Netflix uses S3. So here's what I'm going to talk about today. I'm not going to go over a whole lot of the architecture at Netflix or anything like that. We're going to dive straight into it because it's a fairly technical talk, and I want to leave time for questions at the end. So if you have questions like, how many petabytes of data does Netflix have in S3? Sorry about that. We'll hopefully have time for that at the end. But what we're going to actually talk about is a Netflix use case, so an example use case. Then I'm going to present some performance results using Iceberg versus using just a generic normal Hive table. And I'm going to do that because presenting the performance results at the end really makes you guys wait for the interesting part. So hopefully it'll go, wow, those are great performance results. How did you do that? So that's what we're going for. Then we're going to go through how Hive tables actually work, then what's different and what's new about Iceberg tables, and then basically where the project is at and how you can get started using Iceberg, because I think you'll want to. All right, so starting off with Iceberg performance, here's our example Netflix use case. Netflix has a system called Atlas, and Atlas stores and allows you to visualize basically all of the telemetry data coming in from our runtime systems. So every microservice in Netflix has a little component that sends metrics every minute to our Atlas service, and Atlas is responsible for allowing people to visualize those metrics. So there's a ton of data, and it's also typically doubles or something that's really large to store. Now, to give you an idea of how large this is, when we move that data from the runtime system that gives you a 2-week view of what has been happening with our runtime systems, 1 month of that data turns into 2.7 million files across basically 2,700 partitions. And it is so large that if you wanted to scan, say, a day worth of this data, it turns into about 400,000 tasks. So that's really, really big. And the problem that we have is historical queries over this data set. So we've taken it from the runtime system that provides visualization, and we want to say, have these systems been getting faster over time? Or when was the first time I logged this metric, or something like that, a historical query. Basically, we can't do it in even Hadoop. So here's a sample query that we're going to see some runtimes for. We're basically seeing what tags different metrics had. So we have a tag called type. So this is just extra information a runtime system is sending out about this metric. And we want to see, filter by a metric name, get all the tags for it over a period of just 6 days. So that's really not a very long period of time if you're trying to do historical analysis. And what the actual performance is, in a Hive table, like I said, we get 400,000 splits per day. So this is actually underestimating the number of splits. And an explain query for this query right here. We say explain that, and that will actually go out and plan and get all of the splits. That alone takes about 10 minutes to run. So not even running the query itself, not processing the 400,000 splits per day, that takes 10 minutes just to run that portion of the query. And this is essentially why it's so hard to actually process data in this table and effectively impossible, because we have to spend 10 minutes just planning the data and then way, way more time actually going out and looking at it. So With Iceberg, we've made several improvements upon this. First of all, Iceberg has the ability to more easily combine splits in a reliable way. So a lot of the times when we have different read paths in different applications, we have, say, the way Pig reads this table, the way Presto reads this table, 2 read paths in Spark, etc. Getting split combining across all of those paths is really an annoyance. So you might be able to process in one system where you've got the settings right, and you just can't in another system. Well, with Iceberg, we actually have Iceberg handle all of the combining, and that gets the 400,000 something splits per day into just 15,000 splits. Then we want to attack really that 10 minutes of wall time just used for planning. And what we can do is we can get that down to 10 seconds using Iceberg to track our table metadata instead of the Hive Metastore and S3. So that's a significant improvement. The actual wall time of an Iceberg run is 13 minutes, which is maybe 20% longer than simply planning the query with a normal Hive table. Last, we've added not only partition data filtering, but with Iceberg, we've added extra metadata, and those are the min and max values for every column in the table. So for every file, we know each column's min and max values, and using that, we can eliminate a lot more of these splits. And what was happening before is Spark would start up a task, read a split, realize there's no matching data in that split, and close back down. That actually takes time, and it ends up taking about 12 minutes worth of time. So if we eliminate the splits by doubling the planning time going from 10 seconds of planning time to 25 seconds of planning time, then we end up with just 42 seconds for this query over 6 days worth of Atlas data, where we previously couldn't ask large questions at all. So this is something that our Atlas team is actually super happy about, because it means that they can actually have historical queries over the entire Atlas data set, and they don't take days or weeks to accomplish. Okay, so that's the motivation for this talk. Really, the rest of this is, how does Iceberg work? How do we do this? And really, what's wrong with the way we're currently storing table information, and what can we do to fix it? Sound good? Great. All right, so first off, we're going to go into Hive tables, how they work, and what basically the design challenges of them are. What's causing this to take forever? So the first thing to cover here is the most common question we get about Iceberg, which is, what the heck is a table format anyway? Everyone knows what a file format is, right? It's however you decided to take data and put it in a file as bits. But what is a table format? What am I actually referring to here? What I'm talking about is how we take those individual data files and bundle them up to have this high-level concept of a table, right? So a table of rows and columns, those have to be stored as files somehow. And the question is, how do we do that? How do we get all of these files to look like a table? Well, Hive is based on a very simple idea. And that idea is that we just organize the data in a directory tree. So you can imagine in the early days of Hadoop, we were like, oh, a table is just a file, or maybe we need multiple files. So a table is a directory. Oh, if we read the entire directory, it takes way too long. So let's put subdirectories. We'll put each day worth of data in a subdirectory. And then we'll put each hour worth of data in a subdirectory. And that allows us to take a query and say, if I have a filter on date, then I can go to the top level directory. And if I have a query on hour, I can go into one of its subdirectories and ignore all of the rest of the data. So this is basically more or less how Hive tables work today, with one critical change. The problem is that if you only have this data in the file system, you have way too much directory listing. So if we have 5 years worth of data, that's 360 partitions per year, times 5, times 24 hours in a day, times however many other partition levels we want to go down. So we get way too much directory listing just to do things like read the last day worth of data, where we should be able to go and directly say, okay, I know the last day is out there, just give me that. So the solution that we've turned to is to use the Hive Metastore. And I'm sure pretty much everyone in this room has touched or used the Hive Metastore before. Most of this is hidden from you, but what it does is it has a table of partitions, and that table has something like a partition key here, where we have date equals 2018-05-13, and hour equals 19, and then that points to some location in HDFS or S3 or some other file system. That way, we have a very quick database query to know which partitions are there because we've already gathered all of that information. Then we can even filter them if these strings are filterable. And that actually turns out to be kind of a sticking point because it's difficult to plan your partitions so that you can always filter on these strings. But most of the time, you end up with predicate pushdown inside the Hive Metastore, right? That gives you a list of partitions, and now instead of listing all of the directories in an entire table prefix, we can just go out and list the directories that contain data that we want, which is great, except that we still keep track of all the files in these partitions by going to the file system, right? So the file system is still holding data and basically telling us what is in this table. So in other words, we have this top problem. The table state is stored in 2 places. It's stored at one level of granularity in the Hive Metastore. So we have a list of all the partitions in a table in the Hive Metastore. Then we have a list of all the files in those partitions in a file system. So we have a transactional database on the one hand, and then we have a file system on the other hand. And that gives us a ton of problems, mainly because there's no transaction support whatsoever in a file system. And to be honest, there shouldn't be. It's a file system. What it does is well-defined, and we don't need to say like, oh, it'd be great if the name node could make these 5 files, or rename 5 files at a time, or rename a group of files at a time. That's a misuse of a file system that is required because we've got this problem here. That if we want to make changes to multiple directories or multiple partitions in a table, there's no way of doing that without simply repointing all of those partitions, right? So we could rewrite all the data in 5 partitions that we want to change at the same time and then point to the new locations, but there's a ton of duplication work that's happening there, and it's a huge pain to manage that interaction. So we've got this fundamental problem of state stored in 2 places, but it gets worse too. If you want to do anything because of this lack of transaction support, like atomically append data to multiple partitions, you have to do that while acquiring a lock in the Hive Metastore, making all of the changes, and then releasing that lock. That's the only way that you can actually have atomic operations using the Hive Metastore tables. And that's pretty terrible, largely because it requires readers to participate and say, okay, I'm not going to read this table until the writer is done. And the writer also cannot grab that lock until all readers are done. So it's a really bad situation, especially if you want low latency queries. And as a consequence, nothing implements the locking scheme besides Hive. So Hive Metastore and Hive as an execution engine are the only things that actually use this locking scheme. If you're using Presto, or if you're using Spark, if you're using Impala, all of these ignore the locking scheme. So sometimes you just get incorrect results because someone was writing to this table, someone was changing data, and we can't actually make that an atomic operation. All right, and it gets worse. One other thing to note here is that the layout of these files in S3 is exactly opposite to what S3 actually recommends for your file layout. If you want to read a whole bunch of data from S3, they prefer it be mixed up with data that you're not reading, so that all of the blocks that you're going for, or the portions of the S3 index that you're accessing and listing, are on separate nodes in the S3 architecture. But what we've done here is we've forced ourselves into this situation where we have to keep all of these things in sequential order in order to keep track of them for these listing operations. So we basically have a terrible situation for S3 performance. And not only that, it still requires directory listing to plan jobs, where you have O of n listing calls and n is the number of matching partitions. So in our Atlas example, what was happening is we were still listing about 1,000 directories per day of data. So 1,000 directories times 6, we were listing 6,000 directories and receiving or streaming back 1,000 files in each directory in order to plan the job that we were going to run. That's why it took 10 minutes just to plan the job. And what's even worse if you're running on S3 here is that those listing calls may not give you all the files that are in that directory, right? That's the trick of eventual consistency. And this is where we've added basically bolt-on applications to make those listing calls correct. So S3 Guard is a great example in the open source world. Netflix uses something called Semper that does the same thing. Basically keeps a list of all of the directories that were written recently and makes sure that when you list that directory, you get all of the entries. So there are just a lot of problems, and that's what makes it slow. Then there are more problems. I'm just going to pile on. So first of all, we take all of these columns that are partition columns, and we stick them all into a string, which means we have to care about escaping and character encoding. We also store null for some reason as __ hive default partition __, which is super annoying because everyone implements these tables themselves. How hard could it be? It's just a directory of directories of directories. So of course I can implement this myself, but then there are these edge cases that almost no one realizes or actually handles correctly. So that's why if you were using Spark in the early days, nulls were a problem, or just about any of these engines that came up with their own implementation of this Hive table. Also, Hive metrics from the Hive Metastore can get stale because users can just drop files into directories at any time. So there's no reason to trust Hive metrics, and that's why database engines like Presto say, do you want me to trust Hive metrics or do you want me to ignore Hive metrics? Ignoring Hive metrics always gives you the correct answer. On the other hand, it can really destroy your query performance. So it's a trade-off. Ideally, we would like to be able to trust that the metrics handed to us from the table format accurately reflect the data in the table, so we can accurately determine should we use a broadcast join instead of a sort merge join or something like that. Then we've got the Hive Metastore is a scale bottleneck. Most people probably don't run into this, but if you're at, say, LinkedIn or Twitter or Netflix, I'm pretty sure you are. Actually, I don't know that we are. Yes, we are. We're definitely hitting that. And then the table definition is tied to Java for no reason. So these are all minor things that we'd really love to improve. Piling on even more, even if you get all of that right, there are still a few annoyances. So in Hive tables, schema evolution happens by different rules for different file formats. So CSV, for example, is done by the position or the ordinal of a column. Avro matches columns with older data by name. So if you rename a column in one table format, you get different behavior than if you rename a column in a different table format. Super annoying. It's unclear what file formats support which data types. And nesting is a big problem here. I think CSV by default has like 3 or 4 levels of nesting, and after that, good luck, you're on your own. And then the biggest one that I put up at the top is that all of the people querying a table have to understand its physical layout. So going back to our example of data that's stored by day and hour, if I have a query, or I tell the user, you can query this table, and it has a timestamp column, they're going to say something like, oh, I want all the data where timestamp is greater than yesterday at noon. And just that query alone, timestamp greater than X, gives them a full table scan. They're going to read every single piece of data in that table. And that's because Hive doesn't keep track of the relationship between the timestamp column and the date partition column. So Hive can't say, oh, you have a query on the timestamp column. I know that that's really this day, right? So you have to get them to add something like what I have here in this slide. Timestamp greater than X, and my date partition column is greater than the day of X. Or if it's equal to the day of X, then after the hour that I was looking for, right? This is a total pain for users that don't want to know about the physical layout of our tables. So this is a real challenge. We get users all the time that are new to the data platform, but have been working with like Redshift or some other database for years, and they immediately start querying our data. It's pretty self-explanatory. There's a timestamp column, and then we have to say, oh yeah, right. If you're filtering by timestamp, there's this funny thing. You just have to add all these other predicates to your query as well, because the database isn't smart enough to actually get you the data that you were looking for. And their eyes glaze over, and they get 50% of the time, their eyes glaze over, and you have to explain it again. The other 50% of the time, they get super angry and say, I'm just going to use Redshift. Okay, so that's basically the current state of tables in Hive. And I know I've made a lot of complaints here. Let's go into how Iceberg works and what we can do about those problems. Iceberg is essentially looking at this problem of a table format and approaching it and saying, rather than just using the standard table format that's kind of naive, let's actually design something that has the properties of a table that we desire. So things like atomic operations, no matter where you're making changes in the data, right? And minimal operations, because today we can get atomic operations if you're changing whole partitions, but that's super inefficient. Iceberg also has goals of like fixing table schema evolution and all of those things. So let's take a look at how it works. Much like we started with a key idea behind Hive's table design, that was, hey, let's just put stuff in directories and then only use the directories we want. Iceberg's key design is we're going to track all of the files in a table over time as they change. We're going to do that by keeping essentially, in conceptual terms, a snapshot of every state of this table over time as it changes. So think of a snapshot as a complete listing of all the files in a table. It's pretty clear that what we can do here is we can produce a new snapshot, point the table to that new snapshot, and that's a single atomic operation to make basically any change we want at a file level to this data, to this table, right? And that's really cool because we get this other property, which is snapshot isolation, which is why we call them snapshots. We get snapshot isolation. So here, I've got this transition. I've got snapshot 1 that no one cares about anymore because the current state of the table is snapshot 2. I have a reader come, start looking at snapshot 2. Since that's the current state of the table, that reader goes and grabs that location and gets that file listing and starts reading with a complete and consistent picture of the table. Then say at the same time I have a writer come in and wants to make changes. Well, he's not changing any of the files because all of the files are immutable, just like in the old Hive tables. All he's doing is creating this new listing of files, either appending or replacing files or something like that. He creates a new listing completely separately and then just swaps the pointer to the current state of the table. The reader, even after my writer has committed those changes, The reader is probably still working because it takes a long time to read data, and he's still pointed at S2 because that was the current state when he started. So he doesn't get this mixture of states because someone dropped files in directories and he happened to list those directories after files were dropped or anything like that. So we have a very consistent idea of what data is in this table. So any change to this file list is an atomic operation. We can easily append data across partitions. We can merge or rewrite files within a partition. So what if you have a distribution of file sizes where most of them are large, but 10 files ended up being really tiny? We can go merge those 10 files and take care of the tiny files problem without affecting any other state in that table. Okay. But in reality, we don't really want to rewrite the entire state of the table every single time because that would get expensive. So in reality, it's a bit more complicated. So we're going to go into how that works. What we actually do is we have this implementation of Iceberg Metadata that's based on this idea of a snapshot that contains all of the entries or all of the files in a table. It adds schema information, some partitioning strategy, some string properties. It also tracks old snapshots so that we can clean up the files that were removed and are no longer in the current state of the table after some period for garbage collection. It basically adds all of the practical concerns on top of that conceptual idea. So the first thing to note here is that table metadata is immutable and it always moves forward. So even if so here we have version 1 with 2 snapshots in it. Now we're tracking snapshot 1 because remember, great, 10 minutes left. We're tracking snapshot 1 because readers may still be using it. We don't want to delete the files from snapshot 1 yet. So we keep track of old snapshots. Then we add snapshot 3 and that becomes the newest one. And then maybe we go and clean up snapshot 1 at some later time. Now, how does all this work? We don't actually want to keep track of entire snapshots or rewrite all of the data files in a table because this is a list of perhaps 2.7 million files. So what we use are manifest files. And a snapshot of a table is simply a set of manifest files. And the union of the data files and all those manifests constitutes a snapshot of the table. So in this case, snapshot 2 points to m0.avro and m1.avro, right? And snapshot 3 just points to m2. So we've, in this case, rewritten all of it, but we can split across multiple manifests to avoid writing quite so much data. These manifest files, again, on the more practical side, contain basic file info, so the location and format. So we can change the format of a file. Can't change the format of a file, but we can change the format of a table at a per file level. So sometimes we want to use Avro, sometimes we want to use Parquet or Orc. It also contains data for the partition filtering. So each file has a tuple of its partition values, which are full fidelity values. If there was a null in partition data, we actually store a null, or we store an integer or something, and we never coerce to a string in order to store this data. We also have, like I was saying earlier, per column lower and upper bounds. And then we also have per file metrics for cost-based optimization. So no matter what changes about this listing of files, we always have accurate statistics by aggregating across all of the files. I don't think we have enough time to go through commits, but the main idea on commits is simply that we want to maintain a linear history of these snapshots so that two writers don't conflict and make changes to the table and one of them just goes away. So the way we implement this is with that pointer to table metadata. So version 1 must then point to version 2, must then point to version 3, and so on. This is actually the most difficult part of using Iceberg because you need something to implement atomic swap. So if two writers happen to try to commit to a table at the same time, one of them wins and one of them loses. So we have a custom Metastore implementation that does that. Is now it's version 3. Did my finger slip? Sorry. Okay, table metadata was version 2. Now I want to make this version 3, and if version 3 already exists, it fails. All right. We use optimistic concurrency, and if you are interested in those details, come talk to me or let's grab lunch. Let's get into the design benefits really quick and then save the last 5 minutes for questions. So first of all, reads and writes are isolated and all changes are atomic no matter what you make to the file listing. So this gets us the property that tables, right? If we do any operation in, say, Spark or Presto, those operations like overwrite these partitions, something like that, those are atomic no matter what changes we make. We also get this append support that is also atomic. There are no expensive or eventually consistent file system operations. So by keeping a list of all of the files in a table, we eliminate the need to do any directory listing, and we eliminate the need to rename anything in place because we're no longer using renames as this way of releasing data into the table. So all of our expensive operations and eventually consistent operations are eliminated. And we also have way faster scan planning, which I think was clear from the performance section. We can scan 10 manifest files and look for the matching files that we want way faster than we can list 100 directories. All right. Now, the current blocker for anyone who wants to use this is really Hive Metastore support, because you need this atomic operation to say, I think the current version is 2, I want this to be 3. Once we have that publicly available, you'll be able to use it. However, there is an implementation that relies entirely on HDFS and rename operations. Then there are more improvements. We've implemented a new schema system that uses IDs to track columns. So this is what databases like MySQL or Postgres do with their internal data formats. So what you end up with is full schema evolution support. Add, drop, rename, reorder columns, whatever you want to do, these things are supported. That's really cool for users because users hate it when we say, oh, you renamed a column? Well, that works in these 3 systems, but not this other one. Sorry about that. Users hate that. Another thing that users hate that we fixed is reliable support for types. Date, time, timestamp, decimal. We have tests that validate that all of these work the same across any underlying format for Iceberg tables. So users no longer have to care, does this data format support the types that I want to use or anything like that. We also support struct, list, and maps, and any combination thereof. Also hidden partitioning. Iceberg keeps track of the relationship between partitioning values and the columns that they came from. So we get this separation of physical storage from logical data. If I have a predicate on my timestamp column, Iceberg will automatically bake that down into a predicate on my partition data for scanning those manifests and snapshots. So we get basically easier queries for free. And at the same time, we can evolve the layout of the table underneath those queries, because the queries don't themselves depend on the date column or the hour column existing. We can change and move an hourly partition table to partition by day and so on. And we also support reliable metrics. All right, so here's the information if you want to get started using Iceberg. We have an open Apache licensed project. We have a Spark 2.3 plugin that is publicly available. We're working on pig support, and there's a Presto PR coming soon as well. So, keep in touch with us through this GitHub project. I would love to hear from you guys as well. And with that, let's get to questions so you guys have time. Yeah. Oh, there are mics.
So the manifest files, so what is HMS store in this case? Or HMS is not in the picture at all.
So the only thing that we use the Hive Metastore for is this pointer to table metadata. So all table metadata is a series of files. It's a little like a Git repo, where you've got this tree of files that track all the metadata in a table and eventually point to data files. And the Hive Metastore just points at one of the top-level entities in that directory. And that top-level entity tells you everything you need to know about that version of a table. And then just atomically swapping that pointer is what gives us the atomic operation to go directly from one table state to the next.
Okay. So can I go with the second question? If nobody seems...
No one's behind you.
Okay. So are you planning to contribute the snapshot code to Hive Metastore?
So this is currently an independent library that handles all of those operations. I don't think that it's appropriate to put it into Hive or anything else because we're building support for Pig, Presto, Hive. We're trying to push Redshift to support it. Things like that. I think this is really a common table format that should exist on its own and be integrated into those projects as a dependency.
Thank you.
Yep.
Thank you. Congratulations. Is just for Amazon S3, or are there plans to make available for HDFS on-premise? Or
Good question. This works just as well in HDFS as S3. The S3 thing was just purely me trying to market this talk. So I'll call it what it is. So a lot of organizations have the name node as their bottleneck. And a lot of the operations that are expensive in S3 because they're remote calls are also problems for HDFS. So listing operations, that sucks. Rename operations take like 20 milliseconds a piece. So even with output committers, all those renames are taking a significant amount of time. This really lessens the pressure on your name node as well. So it's for HDFS back tables as well as S3 fine with Azure. I think Steve has a great quote saying, if it works with S3, it'll work with anything. So it should work with wherever you want to use it. Yep.
My question, does it work with the previous Spark versions? And also, what's the performance with S3 for transferring data versus data locality? Okay,
so good questions. First of all, previous Spark versions don't support the V2 data sources. What we've done is we've backported that. It's a pretty straightforward, clean backport into 2.1 and probably 2.0. I haven't done the 2.0 backport. So no, but it's not that hard to do it. And then on your S3 question, something that we didn't cover in this is I mentioned that Hive tables have the exact wrong layout. Well, the actual file operations here are unchanged. Reading and writing data is pretty much the same thing, except that by tracking all of the files individually instead of as a partition, we can spread those out using a hash value at the beginning of your S3 key. So we actually have an implementation in here that shards the data really finely across an entire directory. That way, we're basically spreading that out in the S3 index and the S3 blocks. So we expect, once we do some performance testing on that it will show a performance gain, but we haven't done the testing yet.
Okay, thank you.
So you said that you keep track of multiple snapshots just so that if you have concurrent readers and writers, what system do you use to keep track of which users do operations on your table?
So the nice thing is that we don't have to track individual readers. That's one of the things that is problematic about Hive because readers have to participate in the locking scheme. Say, hey, I'm reading this table right now. So what we do instead is we just keep this, we say that every reader should use the snapshot as of when they started. And then we say, well, readers probably aren't online for more than 24 or 48 or 72 hours. So we just have a garbage collection policy that says after 72 hours, or after, I think ours is 7 days even. After 7 days, we're going to assume all of the readers of this snapshot are gone, and it's okay to get rid of that snapshot.
I was wondering whether you can compare Iceberg to Hive asset tables, also to Databricks Delta.
Okay, so Hive what tables?
Asset tables?
Oh, Hive acid tables. Hive acid tables. So Iceberg is for slower moving data than Hive acid tables probably. There's no reason why the metadata model couldn't support something like Hive acid, but we would do it fairly differently because at the point where you're tracking individual files, you could do the operations required by Hive acid a lot more effectively. So instead of requiring bucketing, value and make a delta for that file individually, instead of like all the things that Hive acid has to do in order to make sure that the deltas are applied to the correct files. As far as Databricks Delta, I'm not sure how that works. Source, so it's unlikely that you're going to see Presto support, Pig support, you know, across the ecosystem. So that's why it's. Sorry. Gotcha. We want to have support across a number of projects, so that's really why it works for us. I think lunch is next, so I'm happy hanging out as long as you guys are.
Yeah. So where is the metadata stored?
Where's the metadata stored?
Yeah.
Metadata stored is stored essentially like in a metadata folder in the file system. So like I said, it's kind of akin to Git, where you have this tree of metadata that eventually points to files. We have a metadata JSON file that contains snapshots that point to these manifest files. Manifest files eventually point to S3, and there's this big graph of them. And the Metastore points to one of those metadata files.
Do you go beyond table granularity, like, or if you just have two writers to the same table, that's a conflict and you're done?
So the nice thing about writer conflicts is that the Metastore is what's responsible for this atomic swap, one metadata version for another. That gives us the ability, because that's such a cheap operation compared to what Metastores are doing today, we could design a Metastore that can do cross-table quite easily by saying, instead of like begin transaction, verify that version is X, and then for multiple tables in the same transaction. So I think this gives us a path to.
I think what I meant was, if I, for example, do an update, delete record timestamp X, and somebody says delete record timestamp equals Y, technically they don't conflict.
Yeah, I did. So the slides are going to be up online. Basically, commits are resolved when they conflict. So two commits come in, right? And both of those are structured as assumptions and actions. So the assumption there is that timestamp X, right? So we have one writer says, I delete timestamp X, one writer says delete timestamp Y. The assumption of delete timestamp X is that X still exists, right? And we can do anything else to the table. As long as X still exists, I can delete it, right? As long as Y still exists, I can delete it. So basically, when we apply these, we go grab the new metadata and say, okay, are my assumptions for this version valid? If so, do the actions and try to commit that. So that allows us to, even though we had commits that failed, it allows us to apply those changes no matter what order they came in.
So how does ingestion into this framework work? Like, I'm assuming if you have pre-existing data, you're going to want to be able to ingest this into the file-based
Right.
tracking system.
So right now, we're supporting basically implementations in query engines. So Presto will eventually be able to write. Right now, Spark can write to this table format using the data frame API. So you can say, take this data frame, write, insert into table T, and it just works. However, one of the things that we're purposely not doing is making it so that you can just drop files into a directory and have those show up as data in your table, right? So in that case, what we would want to do is build like a NiFi connector or build support in one of these engines. So you drop a file or you drop 10 files, and then you go do a metadata update. Now that metadata update goes through the Iceberg API, and the Iceberg API handles all of the, the commit resolution and things like that.
Just a quick follow-up on that point. You just said getting notifications if thing got dropped in a directory. Doesn't S3 send you events that way if you ask it nicely?
Well, so you may get notifications or something like that, but it doesn't automatically become part of the table.
No.
So you can't, one of the things that we want in Iceberg is to decouple physical storage from logical storage. So like users should think about a table like they think about a table in MySQL. They shouldn't think, oh, I can just go muck with the data underneath it. How often are you doing that in Postgres, honestly? So what we want is, you go through the API in order to append data to a table, not just drop data in a magic location.
Okay, thanks.
Yep.
Thanks for the talk. One question, can you put the files, the actual physical files for a table on different storage systems? For example, partition X on HDFS, partition Y on
Yes.
S3, yes?
Yeah.
Okay.
So there are no requirements other than you store a full path in the manifest file. So wherever that is, you can store across HDFS clusters, some in S3, some in HDFS. You can, like I said, you can change the partitioning of files. You can do a lot. The spec is open and is intended to be implemented in multiple languages as well. So you can do a lot of things.
If you have existing data and tables, like S3 tables right now, to transfer it from S3 to, let's say, Iceberg, that would be the question is, the table formats right now, do you only have defined S3? Would that work for the ones on Iceberg, or it has to be like a different format defined for each table once again?
So this kind of goes back to the previous question. Right. You can point to data files wherever they're at. Okay. As long as you have a Hadoop file system implementation that can go read those files,
yeah,
you can point to them anywhere. So what we've done is we have a notebook, and I think this is public on the examples section of our GitHub project, that goes and lists all the files in a Hive table and then creates Iceberg metadata around that. And then you don't have to rewrite any data files to import that data. Now, you want to be careful about having two different opinions of what's in a table. So do that transition once and then stop writing to the Hive table. But that's basically what we're doing.
Do you have any numbers on how long it takes you to verify all of these assumptions when you're doing conflict resolution?
Conflict resolution is actually really cheap, unless you happen to hit something where you have to rewrite one of the manifests or something like that. So it really depends on the operation. If you're deleting files from a table, then you almost certainly you definitely have to rewrite a manifest. So that can be expensive, and it's really the amount of time it takes to do those file system operation on the manifest files. That's the dominating factor. So also on that subject, this is intended for not writing all the time, right? So writes are way more expensive than reads because we're going to read a lot more often. So that's why conflict resolution happens on the write side and things like that. Now we expect it to be less than a few seconds in the majority of cases, but we really, I don't think we have enough data to really say that that's always the case. Yeah.
So you're talking about adding files and removing files from the system. Is there a way to update a subset of the file? So is there a way to run something like an update, SQL update statement on top of the system?
So no, we don't support SQL updates. There's no reason why we couldn't do that. The table format itself considers all data immutable. So the table format would require the query engine to go rewrite that file without those things and then swap the files.
Okay,
So we support that atomic swap across however many files you want to do, right?
Right.
So that's good in one sense. We could also write an extension spec that has like Delta files or something like that so that you can always append new changes like that. Those things don't really exist yet, though.
Okay, yeah, all right, thank you.
This is really just pure table metadata, so we would have to add extensions for those things.
Okay.
Awesome, well, I guess that's it. Thank you guys so much for coming and for staying this late. Thanks.